Okay, so we've got two more lectures left on this course. And that would two possible ways to go. So one would have been to continue presenting core category theoretic notions and constructions and results about them, sort of following on from the lines of what we've been doing up to now. And that would be useful in the sense you'd learn a little bit more category theory. But however far one does that, one kind of never gets to the end. There's always more stuff to present. So I thought that actually instead I would do something different, which is stop more or less the basic category theory now, the main constructions, and talk more about relationships with other mathematical subjects. So particularly today, there is not going to be very much core category theory in the lecture, but it's rather going to be about a perspective that category theory provides on constructions and situations that arise in other mathematical subjects. In this case, a particular focus is going to be complex analysis. So this is a very different area for us. This course has touched on discrete mathematics and topology, algebra, those sorts of areas, but we haven't said anything about analysis at all. So that's going to be a little bit of a departure for today. Just to say, if I were going to take the other approach and continue the category theoretic developments, then the things I would particularly do are Kahn extensions, which were mentioned in the previous lecture and are even covered to some extent in the notes from the last lecture. I didn't have time to go through that part of the notes in the lecture. Ends and coends. Yeah, maybe that would be those would be the main topics and the relationship between those. And then maybe enriched category theory would be something also useful if one were going in those kind of general directions. Right, okay, so what I'm going to talk today about is something called sheaves, which leads on naturally from what we've been doing, because most recently we've been talking about functor categories, especially these functor categories of the form of functors from the opposite of a small category intercept, and that's called the category pre-sheaves over the small category. And the pre-sheaf is there, the pre in pre-sheaf is there for a reason, because the pre-sheaves are something that is not quite a sheaf. A sheaf is a pre-sheaf with an additional condition. And the level of generality that I'm going to cover this topic today is to do with sheaves over topological spaces. And you may think, well, I promised you some complex analysis, and now we're talking about topological spaces, but we will get to the complex analysis quite soon. But first, I want to talk about the general notion of sheaf over a topological space. So let S be a topological space, any topological space, a topological space. And we're going to consider, we're going to define a pre-sheaf related to this. So pre-sheaf needs to be associated with a category. And the category we take here is the category determined by the partial order of open sets. So the collection of open sets is a collection of subsets. It's a partial order under subset inclusion. So I'm going to write O of S for the collection of open sets. The partial order of open sets. So the partial order is ordered by inclusion. I should say really under subset inclusion. Here we go. Put it here. considered as a category. So remember, any partial order was a category that just has one morphism between the objects and the elements of the set, and one morphism whenever the two elements are related. They're considered as a category. So before I was underlining a partial order when I consider it as a category, but let's not bother with that anymore. So I'm going to define a particular pre-sheaf on this, which is a particularly natural and interesting one. So whenever you have topological space, one looks at some sort of spectrum of it sometimes, which is the collection of continuous functions from the space into the reals. It also makes sense to look at the collection of continuous functions at any point locally in the space. So that's what we're going to do. We're going to look at, so for an open set, so we can write that as the U, one of the open sets of the topological space S. I'm simply going to define CU to be the collection of continuous functions from U to the reals. So F continuous. And this, so this is associating to every open set a set. So it's like the object action of a pre-sheaf, although we haven't yet seen its pre-sheaf, but this is naturally a pre-sheaf. So C defines a pre-sheaf. So remember, a pre-sheaf is going to go from the opposite category of the open set S into set by, well, this works very easy, that if you've got two open sets and U is a subset of V, well, the functorial action maps this unique morphism to, well, we need to map C of V, the continuous functions from V into the reals, onto C of U, the continuous functions from U into the reals. And there's an obvious function that does that. If you've got a continuous function on V, then you'd restrict it to a continuous function on U. So F maps to F restricted in English maths one. I know in Slovenian, I think you just write a bar for restricted, but in English maths one often uses this sort of hook symbol for restriction. So F restricted to U like that. It's very easy to see this is functorial, and so we have a pre-sheaf. Now this pre-sheaf satisfies a further property, and that further property is what makes it a sheaf. And intuitively, this further property amounts to the following mathematical fact, which is to determine whether or not a function is continuous. Determining that amounts to testing it for continuity locally around every point in its domain. So continuity is continuity at x locally for every x. And so the property of continuity is not a global property of the function, but rather, well, it's global because it needs to apply everywhere, but the property that needs to apply everywhere is determined locally. And because of that, continuous functions enjoy the property that if you've got a bunch of continuous functions on open subsets of a larger set, and those continuous functions agree wherever the open subsets overlap, then you can glue all the functions together, you can amalgamate all the functions to get a continuous function on the whole set. So let me write that down as in mathematical detail. It's a little bit complicated to write down, but the conceptually it's not so difficult what's going on. It's really amounting to this local property gluing the functions together. So we can write this as follows, that suppose we've got a family indexed by, it doesn't really matter, any index set is a family of continuous functions. Well, all these U sub i's are open. I'm not going to write that down, but I'm going to use U to as the notation for open sets. And suppose these continuous functions agree whenever two of their domains overlap. So if you've got any intersecting domains, then they agree on the intersection. Satisfying that for all I and j in the index set, if we restrict f of I to ui intersect uj, so if you consider f of j, which is the function from, so if you consider fi, which is the function from ui to the reals, and f of j, which is the function from uj to the reals, we restrict those to the intersection set, then they agree with each other. And in this case, we can patch all these functions fi together to get a continuous the function determined by patching all the fi's together, which makes sense because of this this property here, which is called that the family is matching. That's what we say, that this means that the functions match. The function that is then defined on the union of all these domains here is again a continuous function because continuity is determined locally. So we can say that, but then the function let's write U for the domain. Well, we can define U in the following way. It's determined as the unique, sorry, not U, we can define the function we want to define on the union set U in the following way. There exists a unique function f from U to the reals, continuous function, that's important. Such that this function agrees with fi whenever we restrict it to ui. So such that f restricted to ui equals f sub I for all index elements I, where u, as I said, is the union over the i's, so the union of all these domains of the f sub i's. Okay. And this property says that C, this pre-sheaf, so from the opens of the space opposite to the functor, from the opens of the space opposite to set, is a sheaf. Okay, so it's not a mathematically deep property, but it requires a little bit of a cumbersome formulation. The reason for formulating it in exactly this way is because the same property can be made sense of for an arbitrary pre-sheaf. It doesn't always hold for a pre-sheaf, but you can formulate this. The formulation I've used here essentially only involves the pre-sheaf structure. It doesn't really use the fact that we're talking about a particular pre-sheaf, the pre-sheaf of continuous functions. So I now want to formulate that, the notion of sheaf at that level of generality. So maybe I'll go to the other board. We're still working with an arbitrary topological space, and let's let P be any pre-sheaf. P, so that's a functor from the opposite of the open sets into set, the any pre-sheaf. But pre-sheaves are just functors of this form. We say that P, oh, actually, in order to say that it's a sheaf, we're going to basically formulate the same notion. So I want to again say, whenever we have family of elements in P, so the functions, these functions from the domain here, these were elements of the sheaf C locally at U. This is an element of C of U. And I want to say, whenever we have a family of elements that satisfies a property like this, which is matching, as we call it, for any such family of elements, there exists a unique property, this, which is a way of gluing together these matching elements. And the terminology we have for that is a unique amalgamation. So I'm going to first define those two notions, what it means for a family of elements to be matching and what it means for a family to have an amalgamation. So a family of elements xi belonging to P of ui, again so a family of elements locally from the pre-sheaf indexed over objects of our category here, which are open sets. So before these were continuous functions from ui to c, now they're just arbitrary elements of the pre-sheaf P. And continuous functions for elements of the pre-sheaf F. So it's matching if, well, basically the same property we had before. So if for all ij in the index set, if we consider xi and restrict it to the intersection of ui intersection uj, to the intersection between ui and uj, that's the same thing as xj restricted to the intersection ui intersection uj, but these are both elements of P of ui intersect uj. Now, there is something I'm doing a bit funny here, which is, what do I mean by restriction here? Because we're no longer talking about functions. We've got an element, each xi is an element of the pre-sheaf over ui. And I want to make sense of the notion of restricting that to an element of the pre-sheaf over a smaller subset than ui. And this is, of course, defined using the morphism action of this pre-sheaf functor. So the notation is where for any x in P of u and some other open subset V, which is a subset of u, we write x restricting to V for the element we get by applying, so this V is a subset, is an open subset of U, so that's a morphism, there's a unique morphism from V to U in the category of open subsets of S, and by the contravariant action of this functor, we can apply P to that unique morphism from V to U, and apply that to the object, to the element X in PU, and we get back an element of P of V. Okay. So this is simply applying the functor action of the pre-sheaf the morphism action of the pre-sheaf. But it's nice to think of it intuitively as restricting an element. So it gives, you can think of in this case, where the pre-sheaves are defined over this family of open sets, this category of open sets, you can think of the morphism action as being a sort of generalized notion of restriction, where the elements we give it are not necessarily functions. They might be, it's any abstract elements from a pre-sheaf, but still the functor action gives us a notion of restriction. So we have the notion now of a matching family, and we want to say that every matching family can be glued together in a unique way. So every matching family has a unique amalgamation. So we can say what the amalgamation of a family is, and then the sheaf property is simply going to be every matching family has a unique amalgamation. So, a family of elements xi from got a family of opens ui. We'll be considering for each ui an element of that pre-sheaf at ui xi. So again, we've got some index family here. Yeah, I want to stick things in a different order. Let's just start again. I want to say an element x in P of U is an amalgamation of a family of elements xi in P ui's. So we're considering lots of local elements in the ui's, and we want to amalgamate them. So well, firstly, U needs to be the union of all the ui's. So the amalgamation is necessary, and necessarily an amalgamation is necessarily an element in the pre-sheaf over the union of all the sets that we're indexing in this family, such that it needs to have, it's an amalgamation of all these local elements, if you like, on this cover, the UI cover of U, if whenever we restrict it to any of the UIs, it agrees with the xi we have on that UI. So such that for all elements in our indexing family, if we restrict x to ui, we get xi. So these are elements of P. These are both elements of P ui. So it's the same property we had here. A little exercise, which is not difficult, but in fact it's very straightforward, but it's a good exercise for getting your head around it, these ideas, which is that if a family has an amalgamation, then it is necessarily any family that has an amalgamation is necessarily a matching family. So you can't try to look for amalgamations of non-matching families. And intuitively, this is like if you go back to the example of continuous functions, if you had some continuous functions that didn't overlap on the intersections of their domains, well, there would be no way of finding a function that glues them all together. So in order to look for something that glues an elements of a pre-sheaf together, it's necessary that the family is matching. So if a family has an amalgamation, then it is necessarily matching. That's an exercise. we can now define notion of a sheaf. A pre-sheaf P is a sheaf if every matching family has a unique amalgamation. So here we're talking about the special case that we're looking at pre-sheaves defined on the open sets on the category, which is the partial order of open sets of a topological space. I've given the same definition of sheaf can be made sense of much more generally than that, but for the sake of this lecture, we're going to be concerned with this case that we start off with a topological space. Right, so we've already seen one example, a very motivating example of a sheaf, namely the sheaf of continuous functions into the reals. So let's give some more examples of sheaves. Let's see if want a bit more space on the right here. In fact, maybe I'll just carry on down the board. So, for examples, well, you may have noticed when I defined the sheaf of continuous functions into the reals from an open U, so locally at U, there was no particular reason to use the reals as the target space there. So, for any topological space T, we can have the sheaf that I call C sub T, where the set of C sub T U on an open set subset U of S. So we've given a topological space S, which we're looking at at examples of sheaves on that topological space is. So it's now simply functions from U as a subspace of S to T, such that F is continuous. Just write F continuous. Okay, and that's a sheaf for the same reason as before, because continuity is the property of continuity is determined locally. So also we can look for any set X. We can look at what we might call Fx of U, which is the set of all functions from U to X, where F is a set theoretic function. So we don't need to worry even about continuity. We get another example of a sheaf here, because the property of being a function is again something that is determined locally. In fact, this is a special case of the previous, because for any set X, you can put the smallest possible topology on it, called the indiscrete topology. Very nice, very silly topology. It only has the empty and whole set as its own. Those are the only open sets. And then the continuous functions are exactly the set theoretic functions. Anyway, it's not a particularly interesting mathematical example. One gets more interesting examples if one looks at specially good topological spaces. So, for example, for any smooth manifold, take your favorite definition of smooth manifold, depending on how much continuous differentiability you require. So if S, so if we restrict to the case that our background space S is a smooth manifold, if S and T are smooth manifolds, then we have a sheaf of smooth functions. Let's call this S sub t, the sheaf of smooth functions defined on an open set U, which are, again, functions now from U as a subspace of the manifold S into T, the smooth manifold T, such that F is smooth. Using the fact that if we've got two smooth manifolds, we have a notion of smooth map between smooth manifolds. If you're not so familiar with differential geometry, don't worry, we're not going to really talk about smooth manifolds anymore. I just want to give this as an example. And again, the reason that this forms a sheaf is the same as before, which is the smoothness property is amounting to a certain degree of differentiability, depending on your notion of smoothness in the manifold. And again, differentiability is something that is tested locally for a function. So differentiability is determined by the behavior of the function on local neighborhoods of a point, of any point in the domain of the function. So that's another family of important sheaves. And analogous to this, that if S and T are complex manifolds, so complex manifolds, we're locally covered by open sets that have charts from open sets of the complex plane, and the maps that take you from one chart to another chart of the same overlapping open set are holomorphic functions. Then we have the notion of holomorphic function between complex manifolds, and again that's a property that's determined locally. So let's call that H sub T of U, which is now again all functions from U to T. F is holomorphic. So the point is, sheaves are allowing us to gather together functions, collect them together, functions that are defined locally, when they enjoy this property that the qualifying condition for being a function in the set is a locally determined one, and therefore when we have a collection of such things that agree whenever they intersect on their domains, then we can glue them together because the qualifying condition is local. Okay, now this is the main example I want to look at today, except let's make it simpler because manifolds are complicated things to deal with. So for the sake of being able to carry on with this lecture at an appropriate level, one that I'm comfortable with as well, I'm going to just make S the topological space of complex numbers, and T the topological space of complex numbers. So we're now going to consider in particular S is the space of complex numbers, and T is also the space of complex numbers. So H of U is now an open set of complex numbers, is the collection. Let's now use H. This is going to be holomorphic functions, what it was before, but anyway, I'm now going to start using H. So it's all functions from U, all complex valued functions that are holomorphic. So defined on the open set U and are holomorphic. And again, these form a sheaf for the same reason as before. So at the risk of being a bit repetitive, just going to very briefly write down again what it means to be a sheaf, but just in words. So we're defining H from the open subsets of the complex plane, opposited to set. So for every open subset of the complex plane, we're going to have a set of things, and that set of things is the set of complex valued holomorphic functions defined on U. So by the way, I hope everybody knows, so holomorphic means differentiable in the complex analytic sense, so in the complex sense of differentiability, and it's enough to be differentiable once and then you're differentiable infinitely many times. I guess there's a similar mode in sloping to holomorphic. Oh yeah, okay, jolly good. I've never encountered this in conversations before, so I don't tend to talk about complex analysis. So this, we've defined this just to say it is indeed a pre-sheaf, because if f from U to H, from U into the complex numbers is holomorphic, so is any restriction to an open subset of U. So for any V subset of U. And it's also a sheaf. But it needs to be a pre-sheaf in order to be a sheaf. There's also a sheaf because holomorphicity is defined locally. So we can amalgamate matching families of complex functions. And just to say it, essentially, well, I'm not going to move the camera. If we go back to the examples, that similar considerations underlie the reason that all these examples we've given form sheaves. I'm saying that because there was one point I meant to raise when I wrote down these examples that I forgot to raise, but which is an important one, which is you will have noticed that all the examples of sheaves I've given are of the form of families of functions defined on the set, defined on the open set. And there's actually a very deep reason for that. And that deep reason is going to be one of the things that we're going to come to at the end of the lecture. So any sheaf has to be more or less of this kind of form, as it turns out. Anyway, let's go back to the sheaf now of holomorphic functions defined locally on open subsets of the complex plane. And what this sheaf satisfies is a property that is not typical of sheaves at all, but there's a very important property which is fundamental to complex analysis, which applies specifically to this sheaf. And this is the following property. So H satisfies also given any H from U to C, so in other words, an H in a holomorphic function, little h in the sheaf at U, and any connected open subset V there's a superset of U. Holomorphic functions have the amazing property that you can extend them to open supersets that are connected in at most one way. You might not be able to extend them at all, but if you can extend it to a larger function that agrees with this one, then you can do so in at most one way. So there is at most one, actually I'm going to call this U prime. There is at most one H prime from U prime to C, or equivalently H belongs to U prime, such that H prime restricted to U equals H. It's not true for sheaves of continuous functions, or in general for sheaves of differentiable functions. It's a remarkable property of holomorphic functions. And this leads to the notion of the analytic continuation of a function, where you have a holomorphic function that you've got defined on some little local area, and you extend it as far as possible to a holomorphic function defined everywhere you can possibly define it. And an very famous example of that is the Riemann zeta function, which is the analytic continuation of the Euler zeta function defined by a power series expansion. So, where the Euler zeta function works, and then if you extend that, Riemann extended that to as far as possible to the complex plane. So we have the notion of the aim of the idea of the analytic continuation. Analytic so extend a given holomorphic function U H from some given open subset into the complex numbers to as large as possible domain. So it should really say to an as large as possible, and hyphenate as large as possible because I've turned it into an adjective. So an as large as possible domain, connected domain containing U. But I won't. This is kind of the idea which works for the Riemann zeta function. We want to, given a function that's defined locally, we want to extend it as far as we possibly can. However, this is too naive. This idea, as I've formulated it, is naive and doesn't quite work. You can't find, in general, as large a possible domain as a subset of the complex numbers for which this works. So I think that's a good point to break. You can think about that. We'll have a break for 15 minutes. And so we start again, 1:15. I see, the hour is completely wrong on that clock, but the minute hand is pretty much in the right place. I only just noticed that. So anyway, it's we shall start again at 11:15 according to the actual time. And in the meantime, if you'd like to ask some questions on the homework, feel free to do so. Okay, so at the end last time I mentioned the naive idea of analytic continuation. You've got some holomorphic function defined on an open set, and you want to extend it to as large a possible domain of complex numbers. But that formulation is too naive. Does anyone know why? What I'm referring to here? So the point I'm referring to is this, that Some analytic functions, if one tries to extend it, one gets inconsistent. Then you try to view the domain as a subset of the real number of the complex numbers, you get inconsistent values. So the simplest example, I think, or a very simple example, is the complex logarithm function. So if you consider this on the complex plane, it's going to have a pole or a singularity at 0. So here we have 1, here we have -1, I minus I. So one possible value that the complex logarithm function can take at 1 is, of course, 0. So we're going to have so one version, if we're viewing the complex logarithm function defined locally on an open subset, we can consider some open subset around 1, and we'll have that the log of 1 is 0. And then to analytically extend it, we want to enlarge this domain, if we like, but we can also consider enlarging it by sort of moving our focus of reference around and seeing how we're forced to extend the function as we modify the power series as we go along. And if we push this bubble this way around, then when it comes to around -1, we're going to get, from taking it in this direction, everything has to be holomorphic along the way and agreeing on overlapping patches, so to speak. So when we get this way, we'll get the log of -1 is I pi. But if you go this way around, then we're going to start going into I times negative numbers to get here. We'll get the log of -1 is minus I pi. And actually, if you keep on going around the circle, if you go this way around, you get higher and higher each time. Each time you get back to here, you go 0, 2 pi, 2 I pi, rather, 4 I pi, and so on. And the other way around, you go negative. So the point is, there is no maximum domain of complex numbers on which it's defined, and it's really wrong to view the domain of the complex logarithm function as a subset of complex numbers, because its true domain geometrically is like an ascending spiral, a bit like a ramp you go up like a spiral staircase in a castle or something like that. I'm not going to draw a picture because I tried to when I was writing the notes, and I didn't like what came out. So the true analytic continuation defines it on like a sort of geometric surface called a Riemann surface, which is a complex manifold that projects down to the complex plane. So the full analytic continuation, you can describe the manifold rather simply. So as I say, it's like a sort of spiral staircase, or sort of going up to infinity in all directions, and we can describe that by giving the, what order do I put things in the notes? Okay, by giving you a pair of real numbers, the second one positive, where we can view this actually as just giving polar coordinates for the complex number, because polar coordinates are exactly defining this sort of spiral phenomenon. If this is the angle part and this is the radius, this is the modulus, this is the angle part, or the argument as it's called, of the complex number. And as we go round, the polar coordinates have this property that the angle goes up from 0 to 2 pi and so on, and down in the other direction. So here, this lives over the complex plane by the map that assigns map that maps every polar coordinate to its associated complex number. So theta r goes to r times e to the I theta. And then here we have the true complex logarithm function, as it were. So for any complex value here, the possible complex logarithms for it are, you look at the fiber over the complex number here, which is going to be, you know, some countable, either empty at 0 or some countable set of complex numbers differing by 2 pi i's or something like that. I'm not, should think about that more carefully, but anyway, you get a countable number of options for here and a countable number of possible values. And so here theta r gets mapped to the natural log of r plus I times theta. And that gives us a complex number. And this is indeed the correct logarithm function, because if we map here z to e to the power of z, the complex exponential, then we get a commuting diagram. Okay, but the point is we've got this sort of so this is somehow the true domain, so to speak, of a complex logarithm, geometrically speaking. And this was what, these kind of observations were what led Riemann to the theory, develop the theory of Riemann surfaces, where these domains are Riemann surfaces, they're complex manifolds living, in this case, over the complex numbers. So what do I want to say about this? Right, so this picture turns out to have then an important topological property, which is very closely related to this space up here being a complex manifold. And this is that this map down here enjoys a property that it's what's called a local homeomorphism, or another word for that is étale. So the left-hand map here which I don't want to write it out every time, so I'm just going to call it P. P is a local homeomorphism. Or another word for that is étale. Étale in French. And what this means is for any y the domain, I'm just using y for a pair here, and open neighborhood of y. No, sorry, for any element in the domain, there exists a neighborhood of the element for which this function restricted to that neighborhood is a homeomorphism, namely an isomorphism of topological spaces. So for any y, there exists an open subset, an open neighborhood of y, such that P of V is itself open. So that's an open subset of complex numbers, and P restricted to B, to this open subset of Y, so that maps P to P of V is a homeomorphism. And this, in fact, explicitly exhibits this space as a complex manifold because these open subsets here, when we take their image under P, are giving the complex charts for neighborhoods of points in the domain. So it's not exactly the definition of complex manifold, but actually this is enough to show that this space up here is a complex manifold. But the point at a higher level that I want to focus on is that we've gone from what we started off with. Sorry, I should move the camera, but I'm over here. I'll move the camera in a moment. So we've gone from what we started off with, which was this sheaf H of holomorphic functions defined locally on open subsets of the complex plane. And now we're looking at a particular complex function, the logarithm function. We've seen that the logarithm function, in order to consider it, so the original sheaf view was look at the complex logarithm function locally, how it's defined on open subsets of the complex plane for which it can be consistently defined on. So we'll have like a bubble like this, and we'll have all the different bubbles that we get by taking this bubble around the spiral and in the other way. So all these local views will sort of coincide in that sheaf. Whereas here we have a global view of the complex logarithm function. It's defined as a single function on as large a possible a domain, but the geometric structure of that domain is a little bit complicated. So there's two views, local versus global. And what I want to show you is that this local versus global picture is a general phenomenon for sheaves. We have the notion of sheaf as we've defined in terms of local structure, but there's an equivalent notion of sheaf in which, rather than considering the elements as being locally defined things, we consider the sheaf as a globally defined space over the space. Now, in the notes, I did this by elaborating from this picture to an arbitrary holomorphic function, not just the complex logarithm function. For any such arbitrary function, one can find a Riemann surface, which is the domain of its analytic continuation. And in fact, all of these Riemann surfaces that are the domains of its analytic continuations, they all live together in a single Riemann surface that embodies all holomorphic functions. It's called the universal analytic function, this general surface. And the individual functions arise as the connected components of this universal function. So I may go into that a bit later. I mean, that part really requires a bit more complex analysis in order to do it. But I think what I'm going to do is, rather than showing that in the case of, for now, and then we'll see if we've got any time left, rather than focusing on that picture as regards complex analysis, try to present to you now, going back to the general notion of sheaf that we had in the first part. So the notion of a sheaf as a family, a sheaf as a pre-sheaf that satisfies this property that matching families can be glued together in a unique way, and develop an analogous picture of sheaves, sorry, not an analogous, but an alternative picture of sheaves in terms of a global structure over the space. And what's going to be important are these maps into a topological space satisfying this local homeomorphism property. Okay? Of which we've seen an example. And so maybe, let me move the camera. Maybe I'll just write very briefly. So in the notes, but it's not really category theory, it's complex analysis. So in the notes we have define an étale map from a space which I call curly G, although it doesn't look very curly on the board, into the complex numbers, and a P here, where this is this Riemann surface that I said that embodies not just the domain of the complex logarithm function, but its connected components are exactly the analytic continuations, the domains of analytic continuations of all holomorphic functions. So this is called the universal analytic. That's G function. Again, it's given as a topological space together with a continuous map which satisfies this local homeomorphism property into the complex numbers. So that's a topological space which this map is exhibiting as a complex manifold, namely as a Riemann surface. Now, the thing that's going to hold true in general is that we're going to have an alternative view of sheaves, again, as continuous maps with this local homeomorphism property into the space S that we're defining. Sorry, not that we're defining, but that we're using as the basis for sheaves. So, a more general picture, let's just say generally, or any topological space S, just write for any space S. We're going to look at the étale maps into the space S. Now, there's a natural category whose objects are maps, continuous maps into the space S, which is the slice category of top by the object S. And typically, when you look at a continuous map into S, you're viewing it as a kind of object of a slice category. The idea is that you've got some space T that you're mapping into S, and you're viewing that as a sort of space of fibers, because so it's like an index family of its fibers indexed by S, where the continuity property is ensuring that those fibers sort of respect the topology in some sense. And mathematicians tend to call that such structures bundles. So we call this the category of bundles. Or S. It doesn't matter. I mean, an object, you know what the slice category is. An object here is just a topological space together with a continuous map into S. And the maps are exactly the continuous maps that make the triangles commute. So if we know what the slice category is. And what I'm going to show is there is a functor from the slice category into the category of sheaves on the space S. And this functor called gamma. So what's the category of sheaves? Well, this is simply the full subcategory of pre-sheaves. So pre-sheaves, I was writing pre-sheaves over a category. So the category, pre-sheaves of open S. The category is pre-sheaves of the category for which we call the pre-sheaves of the whole set of open sets. So this is simply the full subcategory of pre-sheaves on the sheaves. Namely, simply throw out the pre-sheaves that are not sheaves and just retain the objects that satisfy the sheaf condition. So any bundle is going to give us a sheaf. And this is defined in a rather simple way, the sheaf. So we want to say what gamma does to a bundle, which is simply a continuous map P from some topological space T into S. And we want this to be a sheaf on this topological space S. So we want to say that we need to define the set of its elements on an open set U of S. So the set of elements on the open space U of S is going to be the set of all functions from S into T, from U into T, that are what are called local sections of P. So remember, a section of a map, we did that when we did split epimorphisms. A section of a split epimorphism is a map in the other direction that's a one-sided inverse. Namely, if you go round the loop to S, you get back the identity. Here, F is not a one-sided inverse to P on the whole of S because it's just defined on an open subset of S. The U here is an open subset of S because our pre-sheaves are over our sheaves are pre-sheaves on the opens of U, on the opens of S. But still, you can obviously state the property that if you go around the loop, you get the identity. So we're going to require that F is continuous. And that we go around the loop, so P of F of X equals X for all X in U. And this is a sheaf, again, because the two properties here, being continuous and this section property, are once again determined locally. So once again, if you have families of such things, you can glue them and they intersect and they map and they agree on the intersections of the domains, then the unique function defined by joining them all together again satisfies this property. So this is called the sheaf of local sections of P. Okay. So here I've defined the action of gamma on objects. These are objects of the slice category. Now exercise for the brave. Well, I know you don't need to be brave. I mean, you just need to. It's obvious how to do it. Just we're getting to a certain level of sophistication here just to get started on things. But exercise define the morphism action of gamma. Now, the main theorem that I want to state is saying, well, so actually we can define a sheaf for arbitrary bundles. This étale property is not playing any role, but it is going to play a role for the main theorem. So let me, I think I gave the étale property in general here, so let me define it sorry, I gave it the specific example here, so let me define it in general. So P as defined there, the P continuous map from T to S is étale. I'm assuming it's continuous already. I'm not going to write that. If the same thing as before, but for any y in T and open neighborhood in T, so open set V to which y belongs. I'm writing the membership relation backwards here. So I've made exactly the same mistake as before. For all y in T, there exists some open neighborhood. There exists some open neighborhood of y such that the direct image of V under P is open. So that's a subset of S. So that's open in S. And if we restrict the function P to this open set V, then that's a homeomorphism. Homeomorphism. For those spaces living above us, that's together with a map down from the space to S, that's a local homeomorphism. In this sense, around any point in T, you can find a neighborhood that's homeomorphic to an appropriate neighborhood of the image in S. So these étale maps, you think they look like such a strong property, being local homeomorphism. You think that this topological space must be forced to be very nice because of this, but actually it's not in general. So even when S is a really nice space, a Hausdorff space, or even a very well-behaved Hausdorff space, it's not the case in general that spaces living as the total spaces, that's the domain spaces of étale bundles, it's not the case that they're Hausdorff. So these are very often non-Hausdorff spaces, and that's just a fact of life. You can't avoid it. But nonetheless, it's giving us a sort of a notion of topological bundle that has this nice local homeomorphism property. And the reason for identifying this property is the following theorem, which is a significant theorem. The functor gamma that we've defined that maps every bundle to its sheaf of local sections, if we restrict it to the full subcategory of the slice category whose objects are étale maps, so that, of course, still gives us a map to the sheaves over S. This is 1/2 of, it's a function in one direction, it's 1/2 of an equivalence of categories. I'm just going to write is an equivalence of categories. That's an abusive terminology because I haven't given the map in the other direction or the natural transformations. But anyway, it extends, if you like, to an equivalence of categories. So here, the category étale of S, let's put it here, étale of S is the full subcategory of the category of bundles, that's the slice category over S, on étale maps. étale bundles. So those are objects. An étale bundle is a specific object in the size category. Okay. So one of the consequences of this theorem is that it tells us that every sheaf over S is isomorphic. So remember, any equivalence of categories is an essentially full functor. That means every object in the codomain category is isomorphic to an object in the image of the functor. So every sheaf, with this local definition of sheaf, over a topological space S, every sheaf is isomorphic to a sheaf of local sections for some étale map. And this is the deep reason that all the examples of sheaves look like sheaves of functions from their open domain into something. Because actually every sheaf is indeed a sheaf of functions which are always continuous functions, and also with this further section property, any sheaf is a sheaf of functions up to isomorphism. So that's why all sheaves look like that. Okay, so we've got 12 minutes. So I think the right way to do this is, what I'm going to talk you through now is not the proof of this, but a little bit of the idea behind the construction of the functor in the other direction. Because this is a deep construction, and moreover, it relates to things in having the example that we had of complex analysis in mind, of the holomorphic functions in mind. It relates to notions that one has in complex, that one sees in complex analysis. For those who know the notions, for the others, you can just understand the definitions in their own right. Right, so I want to define, so I'm not going to bother to write proof or things like that, because, I mean, in any case, it's not going to be much of a proof because it's just an outline, and I'm focusing on one particular point, which is how to define the functor in the other direction. So the other half of the equivalence. I won't bother with the natural isomorphisms. So we're going to define, did I move the camera? No. Yes. So we're going to define the functor lambda, capital lambda, from sheaves on S to étale maps. So étale bundles, étale maps into S. Right, so let's start with a sheaf. Let's call it F. So let F. So any sheaf is going to be a free sheaf in particular. Be a sheaf. And I need to define lambda F, which is going to be an étale map into S. So it's going to be of the form, I'll write it T sub F for the total space, P sub F for the étale function, and of course that goes into S. It needs to be a bundle over S. Now the idea behind this construction, we've got a sheaf on S, so that's assigning to every open subset U a set of things which we think of sort of locally defined elements on the set U. I mean, we know that we know from the theorem, although we're proving the theorem, that fundamentally we can think of these things as functions defined on U, but that's not important. That just might help you with how to think of these things. So we've got a set of locally defined elements defined at U according to the sheaf. we want to turn that into kind of a collection of elements related to the elements of S. And the idea here is we're going to associate to every element of S an element of a set of locally defined things around S as we get them from the sheaf, where we're only interested in the very local behavior around the point that we're looking at. So to every point X of S, we're going to sort of define the fiber of things above it as the local behavior of elements of our sheaf F at the point X on neighborhoods around X. So to do that, given an X, some element X in S, and an open. Let me look at my notes to see how I do it, because I can go on autopilot, but I'll make some mistakes, and yeah. So we're going to consider the set of all. I'm going to call, even though they're not functions, I'm going to call them F. The point of this is we're going to consider. Sorry, this is all elements of the sheaf F locally defined around X. So where U, so for any open neighborhood of X, we look at elements of the sheaf that are locally defined around X. But we're only interested on these elements. We want to identify them if they have the same local behavior around X. We're going to put an equivalence relation on this. So with the equivalence relation, where we're going to relate U and F, so that's one element locally defined around X. We're going to relate that to another U prime and F prime, where so U prime again is a neighborhood of an open neighborhood of X, and F prime is locally defined at U prime. So this, we relate this if and only if there exists some small neighborhood V. Actually, I remember in my notes I call it U double prime, so let's call it U double prime. So some small neighborhood contained in the intersection of U and U double prime, such that it's still a neighborhood of X. And if we restrict F and we restrict F prime to this small neighborhood, they agree. F restricted to U is the same, sorry, to U double prime is the same thing as F prime restricted to U double prime. So if you think of it as continuous functions defined locally around X, but potentially on two different open neighborhoods of X, what we're asking for is there to be some small neighborhood of X that's in the common domain of F and F prime on which the two functions agree. So the two functions might differ in general on the larger neighborhoods, but they need to agree on some small neighborhood of X. And if so, we equate them. In the case of complex functions, actually, when this happens, then F and F prime are going to actually agree on their intersection because of this unique extension property. At least if we just look at least if we just look at connected neighborhoods here, which is sufficient. Anyway, we use this equivalence relation, and we're going to then we call. Again, let's look at the notes to see. So given UF as above, UF as above, we call the equivalence class of U and F. Under the equivalence relation, the germ, like the germ that causes a disease, but I think the right interpretation of germ here is like associated with seeds. So it's like the seed from which things emerge. So this is called the germ of F at X. And the idea is that this germ essentially captures the local behavior of F around X sort of at an infinitesimally small viewpoint. We're interested in it's the behavior of F at X at some arbitrarily small open neighborhood, so to speak. Now this is now where I want to make a connection to the complex case, because in the holomorphic case, the notion of germ is much simpler, because the local behavior around a point X is determined by the power series. I mean, it's not much simpler in some sense, but it has a different formulation. So the notion of a germ can be formulated into and is done, I think the same terminology is used in complex analysis, and the notion of germ in complex analysis replaces this equivalence relation with a power series defining the function locally around X. Anyway, we can now define the space . We can now define the étale bundle that we want to. So our total space F is defined to be the set of pairs of X . And let's paired with its germ, paired with all germs of X at F, where here where this is determined by some U. Hang on. Where F is determined by finding some U in the opens of S, that's a neighborhood of X, and F is some local element in the sheaf derived, some local element of the sheaf at U. So the point is, we're considering for all points X, all locally defined elements in the sheaf around X, but rather than considering those elements themselves, we take their germs, which capture just the local behavior of those Fs at the point X. And of course, this is mapped by the projection function. So that's the first projection. We simply map to the element X. And that maps us down to S. And that's it. So obviously we need to give this a topology. That's defined in the notes, but you can think for yourself how to do it. I mean, you know, if you want to understand this material, it's a good exercise to try to think for yourself how to do this. And then one needs to prove that this is étale, and then one needs to, once we've got this front to back, prove that it is indeed part of an equivalence of categories and so on. But there's a limit to what one can do in lectures. And really the point I want to get across here is that this theorem is establishing this correspondence between sheaves as local structures where we can glue things together, as opposed to sheaves as global bundles defined over the whole space S, where the elements of the total space represent essentially like the local behavior at a point of the local structures that occur in the sheaves here. And from that, we learn that every sheaf can be viewed as a sheaf of functions, namely a sheaf of local sections, and every étale bundle can be viewed as a bundle of germs of a sheaf, because that's what the equivalence of categories say. And a very particular case of this is take this equivalence is take the sheaf of holomorphic functions over the complex numbers defined locally, and the matching sheaf here, the matching étale bundle here, is the universal analytic function. Okay, right. That's time to stop. I just actually maybe before saying, so this was very much sort of specific material. So next week we will use again the notion of sheaf, but I'm not going to draw on any of the topological or analytic material for next week. So the next week's application area will be different. I'm not quite sure what it'll be yet, but it will definitely be different. Okay, so that's the end of the lecture. Thank you. I should stop the recording and